This afternoon I'm talking about the weird world of the very, very small, talking about how scientists try to get to grips with what the world looks like on the smallest of scales. In other words, we're going to be talking about trying to describe atoms. So we know about the world on the millimeter scale. I don't know if you can actually see the TV screen well enough from there. Is it a bit awkward? Okay. So on a scale of millimeters, there's no problem because our eyesight allows us to see structure at the millimeter scale, so we have no problem understanding the world around us on large scales and on millimeter scales. Does anybody recognize what this particular object is? No? That's a pollen grain. It's probably one of the smallest objects you can actually see because it's got a size of a 10th or a 20th or a 30th of a millimeter. So essentially it's too small to see. Alternatively, we could say it's of order 50 microns. Remember, a micron is 1,000th of a millimeter, which itself is 1,000th of a meter. But microns is not small enough for what we need if we're going to go down ultimately to the atomic scale. So we can build things on micron scales, even smaller than we can see. In other words, we need electron microscopes to actually see things we can build, like this particular ratchet wheel, for instance. We really need to think about what the world is made of when we start talking about, for instance, electronic fabrication rather than mechanical fabrication. If we want to build a chip with a whole load of transistors on it because we want our TVs or our tablets or our mobile phones to work, well, the size of the individual transistors in a typical chip might only be, well, if we're going to get 100 million transistors on a few square millimeters, you can see that the individual objects that we're building, the transistors themselves, are only a few nanometers in size. A nanometer being 1,000th of a micron, which is 1,000th of a millimeter, which is 1,000th of a meter. So we're already down to 1 part in a billion of a meter simply fabricating electronic circuits. But we can ask ourselves, well, how far can we go? Can we take any material and cut it in half and cut it in half again and cut it in half again? Can we keep going indefinitely, or is there a limit to the structure of matter? So what is the world made of? And more to the point, how can we tell what the world is made of? What clues do we have? In other words, what scientific investigations can we make that tell us what the world is made of when we get to the very, very small? The Greeks thought they had it sussed. They simply said, well, everything in the world is just made of earth, air, fire, and water. Now, really nice, simple periodic table. If only it was that simple. Life is much more complicated. And a few centuries ago, perhaps you recognize this gentleman, Sir Isaac Newton, who started to pull together our understanding of matter, our understanding of the way things move on the macroscopic scale, our understanding of gravity, our understanding of light, what we eventually came to call Newtonian mechanics, or if you prefer, classical mechanics. So as of a century or so ago, it seemed like we got most things sorted out. We understand that if we have an object, if we move that object, if we apply a force, it accelerates. If we don't apply a force to the object, it keeps moving. The so-called Newtonian laws of motion. Everything seemed wrapped up as of the 16th and 17th centuries. And it looked like the universe, and I mean that in the most general sense, the Earth, the solar system, the Milky Way, everything that's out there seemed to be clockwork. Because Newton said if you push something, it moves, and if you don't push it, it continues moving in a straight line. And gravity will make planets orbit the sun in circles, for instance. And it looked like the entire universe was simply clockwork. Who knows how it started, but it seems to be just running on its own according to the rules of Newtonian mechanics. But when we start looking at matter, we start questioning the idea of everything being just clockwork. For instance, if we look at snowflakes, every snowflake is different, but every snowflake has a particular pattern. Every snowflake has a 6-fold symmetric pattern. Surely that's telling something about what must make up a snowflake. We can't indiscriminately just keep cutting it in half and hope to find the same structure within. There must be some building blocks that make a snowflake, and for some reason or another, those building blocks want to make snowflakes always with 6 sides. Never 7, never 8, never 73, always 6. So that tells us something about what's going on, if only we could figure out what it is. And similarly, when we look at various crystals, if we heat up a metal and then cool it down, a lot of metals will crystallize. And they crystallize sometimes into rather odd shapes. And again, why would they crystallize into odd shapes? It must be something to do with the building blocks that make them up. And if we look at some crystals that seem to be cubes, that means, okay, maybe whatever the building blocks are, maybe they're little Lego bricks, and that's why we end up with crystals that look like cubes. But if that was the case, how can we ever get a crystal that looks like a dodecahedron? That just doesn't make any sense whatsoever. How can the building blocks make this as well as make that? Do we have different shaped building blocks for different materials? The more we look, in a sense, the more confusing it gets, until we can figure out exactly what those building blocks are and how they interact with each other. And I'm not going to turn this lesson into a history lesson, nor a history of chemistry, but between the year 1600 and 1900, various scientists, I'm sorry to say all male scientists, that's the way it was in those days, a whole load of people made discoveries about the nature of how materials interact with each other. If you react material A with material B, you seem to get this amount of material C. That tells us that there are certain ratios between whatever the building blocks are for this element and whatever the building blocks are for that element. They seem to be in particular ratios because whenever you apply reactions, you seem to get patterns in the way different elements react with each other. So all of these people made contributions. I'll just shout out the names for those that can't read them. Boyle, Newton, Lavoisier, Dalton, Avogadro, Maxwell, and Boltzmann all made a contribution to try and understand the nature of what these building blocks must be. But even though we thought we were getting a handle on things up until the end of the 1900s, as soon as the early part of the last century came along, all bets are off, because suddenly it was realized that the rules of the game, the laws that dictate how things behave on the smallest of scales, is not the same as the rules that dictate how things behave in the world around us that we can see on a scale of kilometers or meters or millimeters. When we get down to small things, ultimately we're talking about atoms, it suddenly dawned on people that things do not behave the same way that Newton predicted they would. And again, I'm not going to turn this into a history lesson, but those first 30 years of the last century, from 1900 to 1930, were pivotal in our understanding of the nature of the atom. And again, I'll just shout out the names. You may have heard of some of these already. Becquerel, Planck, Rutherford, Einstein, Bohr, de Broglie, Heisenberg, and Schrödinger. And the last two names in particular, Heisenberg and Schrödinger, pull together observations and hypotheses put by other people and tried to pull it all together in an all-enveloping theory of how we can expect matter on the smallest scale to behave. So we might think of atoms, and perhaps you've seen this sort of picture of an atom. We think the ultimate building blocks are atoms that are, roughly speaking, spherical, and we tend to think of them as a positively charged nucleus, relatively small, and a whole load of negatively charged electrons buzzing around. So that's a quite nice picture, but it's totally wrong. But it's still a nice picture, and we as humans tend to prefer to have a visual picture of whatever it is we're dealing with. The fact that it's not actually like that doesn't really matter. It's still a useful picture. One reason that that's not right is because in this particular picture, all the electrons seem to be doing the same thing. They're all the same distance from the nucleus, and if we were to measure their properties, we would find they all had the same energy. But that's not how actual atoms behave. When we actually investigate the properties of atoms, we find the electrons all have different energies. So rather than this picture, it was proposed by Bohr and others that maybe a better picture would be to think of the electrons as if they were in orbits at different distances from the nucleus. Still not actually correct, but it's better in the sense that it now allows us to be able to say, these different electrons, which are colored differently in this particular picture, they're all different distances from the nucleus, they all have different energies, and we can now start to work out why different atoms interact with each other. It's because of what those electrons are doing and the energies of those electrons. We still tend to have this picture that it makes it look two-dimensional. That picture at the top makes it look like a sort of solar system. except for the fact that there seem to be 2 electrons going round where there would only be 1 Mercury in the solar system, and there appears to be 8 electrons going around where there would be Venus in the solar system. But one thing we should remember is that no atom is actually a pancake. At the very least, it's a set of shells, and this picture at the top is simply a convenient way of drawing it, simply because drawing something in 2 dimensions is easier than drawing something in 3 dimensions. So we really ought to be thinking about the electrons in shells. But even then, we still haven't got the right picture, in the sense that it is still too wedded to the idea of Isaac Newton, whereby we want to think of things in terms of clockwork. We want to think of an electron actually moving around the atom. Although it's wrong, it's perfectly good to explain the periodic table of the elements. The idea that there's 2 electrons in this shell, and 8 electrons in this shell, and 18 electrons in this shell, etc., that allows us to map out the periodic properties of the elements and understand how they relate to each other, and realize that there are currently holes in the periodic table which tells us we haven't yet found this particular element with these particular properties. So Dmitry Mendeleev there was a pioneer in trying to map out where all the elements belong according to their weight and according to their properties, which ultimately is a function of how those electrons are behaving in atoms. But still at the back of our minds, we have this idea that, does that mean the electron is going around the nucleus in the same way that the Earth is going around the sun? Well, it's a sort of useful start, but it's not actually correct. When it comes to describing what's actually going on with an atom, we have to accept the fact that Newtonian mechanics is simply wrong. It does not work. We have to start thinking about the fact that this new theory of Heisenberg and Schrödinger and others, so-called quantum theory, or sometimes called quantum mechanics, this talks about the atom in terms of the probability that particles exist in particular states, the probability that the electron can be found at a particular distance from the nucleus, for instance. That's not the same as Newton, who said if the electron is here now, I can predict exactly where that electron is going to be in the future. Just like now, if we know where Jupiter is in the solar system, we can basically say, well, if I know where Jupiter is now, I can work out where Jupiter is going to be tomorrow or next year, or where it was 2,000 years ago. With atoms, we cannot do that. We can only talk about the probability of, if we make a measurement, this is the probability that we'll get this result. That is a fundamental sea change to the way we think about the world around us. The change from Newtonian mechanics to quantum mechanics was a fundamental change in the way we see the world. And if we want to map out where are we likely to find an electron in a particular atom, we don't find it's in a whole load of circles, we find that it's in a whole load of clouds as represented by these pictures. And of course, these pictures are only a representation of probability of where we're likely to find an electron. It's not actually a picture of an atom as such. It's a representation of probabilities that can be calculated. So there we have the problem. And this was indeed a problem at the beginning of the last century when quantum mechanics was in its infancy. And it's still a problem now. If we want to teach students about this is the way atoms are, this is the way they behave, this is why atoms make molecules, this is why molecules make us, we have to use words because we are human and we speak English. And so we talk about the electrons. Well, what are we talking? Are we saying that they orbit around the nucleus? We're talking about an electron as if it was a particle. We talk about light as if it was a wave. We talk about orbits. We talk about electrons spinning. But always in our heads, we have this idea that, does that mean it's like the Earth spinning? Does that mean it's like the Earth going around the sun? We're using similar words, but they don't have the same meaning. Because all of these words we have invented over the last few centuries, and then along comes quantum mechanics and steals the words, even though they mean slightly different things. And hence there's confusion when you try and talk to somebody about this is how things work on the scale of the very, very small. So instead of using words, should we just use pictures? Well, we can use pictures, and sometimes that helps in an analogy, but we've already said that the picture isn't right. It's not a solar system. and we could represent the motion of electrons in an atom by little pictures of the probability of finding an electron at a particular position, but that's not quite the whole story either. So if words don't really work on describing the world of the very, very small, and pictures are never quite right either, what is the correct way to describe what an atom is and how an atom behaves? Well, there's really only one way to do it as far as we know, and you're not going to like the answer. The answer is not words, not pictures. There's only one answer: maths. Maths, in other words, the mathematics of quantum theory, appears to be the only way we can make sense of how atoms behave. So that particular equation might look superficially rather simple, but it hides an enormous amount of maths behind it. And of course, if we want to teach students about this is the maths you need to understand how an atom works and why it makes molecules and why it makes us, if we want to describe the maths, we end up having to use words and pictures to explain what it is we're doing. So ultimately, we have to use maths and words and pictures if we want to understand what atoms are actually doing. And that's a sort of snapshot of the maths involved. At university level, that's the sort of maths that students have to deal with in order to solve the equations that tell us how is this thing going to behave. What is the energy of this electron in this atom? Why does it emit light of this particular frequency or this particular wavelength? The maths is not straightforward, and that's why it's always difficult to deal with what quantum mechanics is telling us. Here's some quotes from the people who invented quantum mechanics 100 years ago. We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language. If we try and use our ordinary, everyday English language to describe what an atom is, we get confused because we're using words in inappropriate ways. And Bohr said, everything we call real is made of things that cannot be regarded as real. In other words, I believe that this table is made of atoms, and as far as I know, it is solid and real. And yet, when we're dealing with the atoms themselves, they appear to be rather ghostly things that don't actually exist in the Newtonian sense, that they are not tiny little golf balls, they are not tiny little billiard balls moving around each other. They seem to be ghostly entities whose behavior we can predict with mathematics, but that's about it as far as reality is concerned. And yet, in large numbers, they appear to produce what we would regard as real, solid objects. Schrödinger again, atomic physics has shown that atoms have no meaning. That's an amazing statement for a physicist to come out with. Atoms have no meaning, but can only be understood in experimental measurement. This is coming back to the point that quantum theory basically says, well, nothing really exists, but if we want to calculate what would happen if I took this atom and did something to it? What would happen if this photon of light arrived at this atom? What would happen if this molecule interacts with that molecule? We can do those calculations, and we can do the measurements, and we find that the calculations hopefully agree with the measurements. So quantum theory is a useful way of telling us what we're going to get if we carry out a set of measurements. But that doesn't necessarily mean what we're talking about, this nebulous cloud of probability, has any real meaning. And this is the second real problem with quantum mechanics, is interpretation. One problem is the maths is not easy. The second problem is, what does the maths mean? The maths gives us the right answers, but that doesn't help us understand the nature of what an atom actually is. The architect of quantum mechanics was quoted as saying, I don't like it, and I'm sorry I ever had anything to do with it, which is what you'll feel like if you ever have to go further into quantum theory at a later level. Quantum mechanics, in many cases, disagrees with common sense, and that's why people, including myself, sometimes don't like quantum mechanics. It disagrees with common sense. If quantum mechanics says that it's possible for me to stand here, but it's also possible, according to the rules of quantum mechanics, that I take a shift 10 meters instantaneously from one part of the room to another. Newton says, no, that won't happen. Quantum mechanics says it's unlikely to happen, but it is actually possible. And that doesn't agree with our notion of common sense. And there's a number of different aspects of quantum mechanics that disagree with common sense, and that's why, one of the reasons why people have so many problems with it. So, for instance, the main problem is the fact that nothing is predictable. Newton says, if I know where an object is and I know the forces on it, I can calculate what that object is going to do. But quantum mechanics says we can only calculate the probability of something happening. If we push on an object, we can say the probability of it moving forward is this much, and the probability of it moving sideways is this much. And the probability of this molecule interacting with that molecule is this much. But we can only talk about the probability of things happening. We cannot say what will happen under any particular circumstances. The other difficulty is that when push comes to shove, although we think of atoms as being very small objects, technically atoms have no size as such, in the sense that, according to Newton, an electron being pulled by a central object like Earth being pulled by the sun would have a particular orbit of a particular radius. But in quantum mechanics, we, remember, can only work out probabilities. So we can ask, what's the probability that if this is a hydrogen atom, which is just one proton and one electron, what's the probability that the electron is this distance from the proton? And if the distance is small, the probability might be 1%. And if the distance is larger, what's the probability that the electron is a nanometer away from the proton? Well, that's quite a large distance on the atomic scale. So the probability that the electron is 1 nanometer from the proton is smaller. What's the probability that it's 100 nanometers away? Well, it's not 0, but it's a small number. What's the probability that the electron is a millimeter away? Well, it's a very small number, but it's not 0. What's the probability the electron is a meter away, or a kilometer away, or a light year away? Well, it's not 0. It's a very, very, very small number, but it is not 0. So we can't actually say that an atom is contained within a particular volume, because in principle there's a small but finite probability that the electron of any given atom is actually quite a long way from the nucleus. So although we tend to think of atoms as small, strictly speaking they're not, depending on how we define the atom. We can certainly define an atom as, let's imagine a sphere where there's a 99% chance that the electron is within that sphere. Yes, that's quite a small sphere. But we can't define the volume in which we are absolutely sure the electron is contained. So we can only talk about probabilities, and according to quantum mechanics, an electron in one atom could be anywhere. And another bizarre thing that takes a bit of working out is electrons or protons or any particle or any atom or any molecule can be in two states at the same time. That's like tossing a coin and saying, well, it's going to come down heads or it's going to come down tails. In quantum mechanics, it can be both. I'm not talking about it landing edge on. I'm talking about tossing a coin, and until you actually look at that coin, it can be heads and tails at the same time. Perhaps some of you have heard of the paradox of Schrodinger's cat, which takes that to a new level. But basically, quantum mechanics says that you can't necessarily specify that one atom or molecule or particle or anything else is in a particular state with a particular energy moving at a particular speed. It might be that it's in two states at the same time. It's like saying the Earth is spinning on its axis, and it's spinning, as seen from above, anti-clockwise. But it's like saying the Earth is spinning anti-clockwise and clockwise at the same time. Makes no sense whatsoever, because it disagrees with Newtonian mechanics, because it disagrees with our ability to make sense of the world around us. Because for the last, I don't know how many years in your case, you've been trying to make sense of the world by observing the world and seeing what happens. What happens when I drop something? Well, normally it falls downwards. What happens if I throw something? It goes sideways and then drops. What happens under these circumstances? What happens under those circumstances? That's how you build up common sense from real-world observation. But when it comes to something so small, real-world observation doesn't help you. That's why Einstein made this particular quote. Common sense is the collection of prejudices acquired by age 18. In other words, common sense is just an umbrella term for everything you think you know based on your own experience during childhood. By the time you end up as an adult, you think you know what common sense means because you've seen various things happen, and you know that if I do this, I'm going to get hurt. If I'm going to do that, I'm safe. If I do this, it's going to fall over. Observation tells you what is likely to happen under various circumstances. And by the time you're an adult, that is sort of locked in. And then along comes quantum mechanics and throws that away completely and tells you the world actually doesn't work like that. The world disagrees with common sense. So we don't believe that we can have a coin which is heads and tails at the same time, but quantum mechanics does. And Einstein didn't like that. Einstein was not wedded to this idea that probability is absolutely key to the way the real world works at the microscopic level. Some people disagreed with him, some people agreed with him. He never accepted that quantum mechanics basically told us that we could calculate probabilities but could never calculate absolutes. God does not play dice, he said. God is subtle, but he is not malicious. But other people, plenty of other people disagreed, and the proof of the pudding is we are now 100 years later from the early 1900s, and as far as we can tell, that is the way things are. Yes, God does play dice. So how do we know quantum mechanics is right? It goes against everything we know about common sense. So why on earth would we accept something that is so ridiculous that it tells us atoms are infinite in size and a cat can be dead and alive at the same time? Why would we bother accepting such a ridiculous theory? Well, so far, nothing has proved it wrong. Remember, in science, that is not proof. It's very difficult, some would say impossible, to actually prove any theory correct. If you set up a theory, it is possible to show that it's wrong by finding a counterexample. Quantum mechanics has been with us now for about 100 years. It was effectively cemented back in the 1930s. So quantum mechanics has been with us for about 100 years, and for the last 100 years, scientists all over the world have been trying to find a chink in the armor. They've been trying to find something which proves quantum mechanics wrong. And for the last 100 years, nobody has succeeded. So that's not proof that it's right, but it has stood the test of time, like the theory of relativity, like the theory of electromagnetism, for instance. Quantum mechanics predicts results that Newton or Newtonian mechanics simply cannot get right. There are various circumstances, I'm not going to go into details, but there's various situations where it simply could not happen if you apply the rules of Newton. If you apply Newton's laws of motion, Newtonian mechanics, classical mechanics, if you apply those rules, it does not work and does not give you the right answer. But quantum mechanics does. And there's plenty of examples where quantum is right and Newton is wrong. So we have lots of evidence that the world is not clockwork, that the world is dominated by probability. And we can actually use our knowledge of quantum mechanics to actually build microscopes that help us see what's actually going on at the very small level. If we take, for instance, if you think of my hand, the knuckles of my hand, if you think of those as individual atoms, if we bring a very sharp tip down and move it backwards and forwards, so this is supposed to be representative of the last few atoms in a very sharp tip, coming close to the top few atoms of a large material. It doesn't matter whether it's a metal material or a semiconductor material or something else. According to our understanding of, for instance, electric circuits, if we were to keep a gap between those and apply a voltage between the tip and the sample, no current will flow as long as there's a gap between them. So if we apply a voltage and then measure current, the current will be zero according to our understanding of electric circuits. But if we apply the rules of quantum mechanics to this, we find there's a small but finite chance that the electron can actually go from one of these to the other and exist in a state which Newton says cannot exist. And if we use that to actually build a microscope by moving this sharp tip backwards and forwards across a surface, and we measure how big that current is, it turns out that quantum mechanics tells us even if the current is not particularly large, the current is very sensitive to just what that gap is. In other words, if we've got a little bit of a corrugation because the surface is not dead flat, it's one atom and then the next atom and then the next atom and then the next atom, because there's a little bit of corrugation, there's a little bit of variation of the distance between the tip and the sample, and quantum mechanics tells us that the tiniest of changes to that distance gives us a measurable change in the current, which is indeed what we find. So we can build a microscope based on this principle. Fashion yourself a very sharp tip, bring it very close to a surface, move it backwards and forwards, and measure the current that flows when you apply a small voltage. And in the background there's a stainless steel chamber, which is a vacuum chamber. That vacuum chamber has been evacuated to about 10 to the minus 13 atmospheres or something like that, because when we want to image a surface and when we want to image atoms or molecules on a surface, we don't want air molecules getting in the way. We don't want our surface contaminated because there's loads of oxygen and water vapor and carbon dioxide around. So we put it in a vacuum chamber so you can't see the scanning tunneling microscope itself. It's buried way inside this vacuum vessel. But we can use it to take images of a surface. This is what the surface of rust looks like if you look at it with a high enough magnification with a scanning tunneling microscope. Notice the scale bar down here. That is 2 nanometers. A nanometer, 1,000th of a micron, which is 1,000th of a millimeter. So each of these little mountains, the vertical scale here has been exaggerated just so we can see the bumps a little more clearly. If we imagine that each bump is an atom on the surface, we've exaggerated so they look more like mountains, but basically each mountain that we can see in that image is one atom on the surface. This is rust, so it's going to be either an atom of iron or an atom of oxygen. I'm not going to talk you through how we know the difference, but notice that the atoms are not uniformly spread all over this surface. If we had a square meter of rust, the atoms would not be uniformly spread over that surface. There's a group of atoms that are arranged in a particular pattern, in a sort of island, and then there's a gap, and then there's another island, then a gap, and then another island. Notice not only the atoms are arranged in particular ways within that island, but the islands themselves are arranged in a particular pattern on the surface. That's because atoms are interacting with each other, and electrons from one atom are interacting with electrons from neighboring atoms. You can call that chemistry if you wish, or you simply call it the physics of what the outer electron is doing. So this image would not exist under the rules of Newtonian mechanics. The only reason this image exists at all is because it follows what we understand when we talk about quantum theory. The bottom line is quantum mechanics is tricky, and that's why even the people that put it together 100 years ago realized this was a problem. If quantum mechanics hasn't profoundly shocked you, then you haven't understood it. This is a common reiteration of a statement we make to our students. The bottom line is nobody fully understands quantum mechanics. We can use quantum mechanics. We know the rules of quantum mechanics. If, in a sense, quantum mechanics is a toolbox that allows us to do a calculation and get answers and compare with reality to see if those predictions are right. But trying to understand why quantum mechanics works, why can a cat be dead and alive at the same time? Why does quantum mechanics allow that, even though common sense apparently doesn't? And every time people are introduced to these ideas, you come up against the common sense problem, and then you say, that doesn't make any sense, so I'm going to basically put this to one side. Some people are happy to do that. Some people say, I don't understand it, but I'm happy to use it. The toolbox works. It's a 100-year-old toolbox. I know how to use it. So even though I don't really understand what's going on, and some of its results are rather shocking, I will still continue to use it because it's useful. And that's the bottom line. One quote I really like from Einstein, and I would argue this applies if we're thinking about the entire universe on the largest scales, the expanding universe in which we live, or if you think about looking in the opposite direction at the micro scale and thinking about molecules and atoms and the particles that make up the atoms and the particles that make up the nucleus and the quarks and everything that's going on in there. The most incomprehensible thing about the world, and the world can mean anything from the inner world to the outer world to outer space. The most incomprehensible thing about the world is the fact that it's comprehensible. The universe doesn't owe us anything. There is no reason why the universe should be comprehensible to some monkeys that came down out of the tree a million years ago and roamed over the savannah and then evolved into us. Is there any reason why our brains should be capable of understanding the nature of the universe on the largest of the scales or the nature of the universe on the smallest of scales? There's no reason why it should, but apparently it is comprehensible. With a little bit of thought, we can figure out how the universe works. And I'll leave you with this particular image. Again, it's a scanning tunneling microscope image. The scale of the image, the total width of the image is 850 picometers. A picometer is 1,000th of a nanometer, which is 1,000th of a micron, which is 1,000th of a millimeter, which is 1,000th of a meter. So this, of course, is a tiny, tiny, tiny scale, and we can interpret these blobs here as being, well, it looks like we're imaging individual atoms, in this case of carbon. And just to give you a sense of scale, when we've zoomed in with this scanning tunneling microscope, if you think about this particular scale and ask yourself, well, at this particular magnification setting, how big would a grain of sand be if we used that magnification? Well, a grain of sand at this magnification would be approximately the size of the moon. That gives you an idea of how much we've zoomed in this particular image. And whenever I see any such picture that purports to show individual molecules or individual atoms, I always think back to the William Blake poem, which starts with, "To see a world in a grain of sand." And you realize just how much is going on in the tiniest thing that human vision is capable of seeing. So I hope I've given you some insight into the weird world of the very, very small. Thank you all very much.